Hi and welcome to this tutorial on how to use the package RNetlogo to run agent-based models from R and to get data from agent-based models back into R to analyze those data. I'm going to presume that you have some familiarity with both R and Netlogo, although if you don't know how to use Netlogo, you probably still get something from this tutorial, particularly if you're interested in agent-based models. So first of all, I'm just going to open Netlogo to show you what that looks like, just running the application, the program. You can do agent-based modeling or individual-based modeling in Netlogo. This is what it looks like. We have we can open a model. I'm going to use the fire model. It's under Sample Models of Science Fire, and this model is a forest fire. It's a common example that's used. We have a slider with density. I'm hitting setup, and then hit go. You run the model, and trees burn. We've got 57% density of trees in this forest, and every step of the model we see how far the forest fire goes. If you increase the density to 74%, the forest fire goes further. There's a slider at the top. We can decrease the speed or increase the speed of the model, and that's what happens. Every time you hit go, the model runs continuously. Under the code tab, you can see the code behind this model. We have various variables, like here, number of trees that are burned, the turtles in this model, fire or ember, and every model in Netlogo has a function setup and a function go. So what happens when we set up the model, and what happens when the model goes? Every step, every tick of the model. Right, so in R, let's open R, and here's the tutorial on using RNetlogo. So there's a great package written by Jan Thiel. There's a great reference, this particular paper. I'm going to build on those examples, use those examples he provides, and I use them. Now you should install the package. Now make sure you have the RJava and the RNetlogo packages, libraries installed, and then set your working directory to be where your Netlogo jar file is. You can run Netlogo with or without the GUI, and I'm going to run it with here, this example. So first of all, use your working directory to be the path that we're going to look at. If you look at that path, you can see that it's where my Netlogo is located. And then use this function in RNetlogo called nlstart to open a new window of Netlogo. So from R, we can directly open the Netlogo window, and you can see there it is, it's opened. So this is being run through R now. And what this library essentially does is it enables us to interface with the Java application, the Netlogo application. So I know where the model library, the model I want to run is the forest fire, and this file path function, we just essentially write where it is, the subfolders, and you can see it comes out looking like that. That's exactly where it is in my computer. And I load it, and it loads up, and you can now use that model just as you would if you're not using R. You could just use it like that. But we're going to talk to the model from R, so using this function nl command. I'm just writing this text, and you can see it appears in the command center over here, and it just says hello. But you can do much more interesting things with the nl command function. So we can adjust this slider manually, we can set up and go manually, use just doing it ourselves, but we can also use R to do it. So as you can see, I'm illustrating here. I'm just running the function, the model in Netlogo without doing it through R, just manually amending it. But let's say we wanted to do it from R, and we're using this. This is the code in Netlogo, set density 77. That's what we would write in Netlogo. And by clicking it, you can see it's set it at 77, and we've set it up, and then by hitting go, it moves it just one tick forward. But we want to go further. We'll do that in a minute, but let's just say we wanted to do it at 88. We can run all those commands in nl command in a row, and here you can see set density to density in R, which is 88, set up and go, it does it one tick. Okay. Let's say we want to run for multiple ticks. Again, we'll set the density and we'll set up. And this time, we'll, instead of doing nl command, we'll do nl do command, and we say 100 goes, which means for 100 ticks go. And you can see it will move forward eventually 100 ticks. We can see how many ticks by saying NL report ticks, and it says 100. And if we do it again, it won't start again because we didn't do setup, but it will just go another 100. So we now get to 200. And the NL report will produce a R object, which will say, should say 200. There we go. Now, let's reset the densities to 60 and reset up. And this time, what we're going to report is something else. So we remember the global variables burned trees and initial trees. This time we will do 100 ticks, and we'll get the percent of trees burnt by looking at the burned trees divided by initial trees. This will give us a percentage of the number of trees that are burned. You can see that in the Netlogo it has a percent burned box. But if we look at the code, there's the two globals that we're interested in, initial trees, burned trees. These are updated through the model continuously to produce the percent burned. And we will follow that. So just looking through the model here, this is the setup, and we're going to get the initial trees and burned trees information. So let's look at that. So it's doing 100 ticks, and it's now saved the burned. Let's see what it looks like. It's a list, 100 items, elements, and each one is the percent of trees burned at that particular tick. So the last one is 14.98%. You can see on the right it says 15%. Unlist them, there they all are, we can plot them. So we've got the data from the Netlogo model into R, produce an R object. We can just plot that as we would any R object, and there's the percent of trees burned over time. Okay, so we might not want to know, might not know how many ticks we want to run, but we just want it to run to the end. So we can use this do report while function, and there's 5 arguments that we're adding here. So you can see the 5 arguments listed. We're basically saying while there are any turtles, and that's again the any question mark turtles is Netlogo code. While there are any turtles, keep going, go, second argument. Third is what we're reporting, which we've seen above, and then the 4th and the 5th arguments are what we're returning the object to be, and in this case a data frame. So let's do that. You can see it we've set up, and then it's running. It's just going to run until all of the trees are burned, and I've hit faster and it's a bit jittery on my screen. So I'll go back to normal speed, and it keeps burning and burning and burning at 60% until it stops. It's a few more trees to burn. It's still going. There we go, and now we have that data stored as burned. It actually went 656 ticks, and there's the percent burned over time. We collected it for every tick. Okay, so obviously in this model, if you're familiar with it, there's something interesting happens around the 57-58% mark. So let's look at a range of densities. This is more common in agent-based modeling. We usually want to run the simulation many times or adjust a parameter to see how the model varies when we adjust that particular parameter. So let's look over these densities. You can see 57, 58, 59, 60. We're going to store it in burned as a list, and I'm just going to do a for loop here. So for each density, do this command, set the density, set up the model, then do report while what we did above, and we'll just run it 4 times. There's 4 densities. On the right you can see it run, and I've actually unticked view updates, which basically means the model is still running. You can look at the percent burned box, and you can see it's doing it. You can see the ticks are moving, and you'll see the density slider increment by 1 each time. The model is running, it's just running faster because we're not watching the model run in front of us. And it will finish quite soon. We're at 59%, and when we get to the end, 60% now, this is the last run. We'll get all the information in a list, and we'll have a look at what burned looks like. It should be done. Okay. Burned is a list with each tick, percent of trees burned. This is the 4th one, this is density 60%, and then above is 59%, so on and so forth. So we can just use map cbind to create the density column variable, and then I'll use data table rbind list just to make one whole data table 2,000 something rows with the variables tick, percent burn, and density, and just a ggplot of that. I'm just going to do a little line graph. You can't see it because my window's too small, but here we go. And you can see over the time the different densities, how many percent of trees burned, and quite clearly something happens at that 60% mark, or, well, not quite clearly, we'd need to run the model more times for each percent, but there's something happening there. So let's do that. Let's run over these well, first of all, let's run over 100 densities to really try and identify this breakpoint. So for this, we'll do a sim function where we'll change the density, and all we're doing inside is the nl command, the nl do command while, and nl report. And we're just going to return the percent of trees that got burned for every density, not for every tick, just for every density, the final amount, and we can use this sapply function to run this over the 100 densities. And so on the right you can see the Netlogo model is running, and it gets very quickly up to 47, 48, 50, 51%, and it'll slow to a halt at around 56, 57, 58 while it does it. So I'm going to pause the video and come back when we're up around 95% in a moment. Okay, I'm back. Our model is finished. It didn't take very long, just a couple of minutes. And we have all of that data stored in PB. It's just a lot of numbers. It's a whole vector of numbers. There we go. Each one a different percent, and how many trees got burned, and we can plot it in base R here. Very simple. And if I zoom in, there we go. That's what it looks like. This is the percent of trees that get burned at every density, and there's something going on at 60%. So let's replicate this, focusing in a bit more. And we're going to use this function here where I've just put a replicate with that sim function. So this just allows us to replicate the function a number of times, and I'm going to focus in on this 55 to 65% region. And there'll be our new densities, D. And we'll repeat this simulation 20 times for every one of these. So we'll do 55%, 56%, etc. 20 times. And we'll plot that eventually. Now this will take a bit longer because we're doing 220 simulations here. On the right you can see this. So the 55% goes quite fast. It's getting through them quite quickly because it's not burning. Now I just fast forwarded to 65%. We finished. I paused the video because I didn't want to sit through it. I thought it would take 5 minutes, but it took about 10 minutes. I think because I'm grabbing the screen. It probably would take less if I wasn't screen capturing. I think in the past it's taken me around 5-6 minutes. So let's box plot that. It's a list of vectors, and we can create a box plot. And there we go. For each of the 20 simulations, for each density we have the data. And quite clearly there's something going on around 59-60% in this model, which is very interesting. Now that took quite a long time. I'm going to, first of all, what we'll do is we'll quit the application. You have to use this nl quit command. You can't just close the Netlogo model window. And unfortunately what we have to do with this program is close R and restart an R session. So we'll do that. Let's restart R. Okay, we're back in RStudio, and we'll just scroll down to the bit of the script that is the next step of the tutorial, which is parallelization. So that took quite a long time to do what we just did, and we have to do all the same things like load our Java and our Netlogo, but we're also going to load this parallel package. Parallel allows us to do parallelization. I'm going to ask how many cores does my computer have, how many processors it has 4, and we'll make a cluster. This is just standard parallel package stuff. And what we're going to do now is make three functions. We're going to make an initialization function, which is straightforward. We've done it above. Just load the model, but we have to do it for each processor. And then we're going to make a simfun, which is a function to do the simulation. And it's what we wrote above. It's pretty much the same thing, but I've embedded the sim function inside of. I just want to have one function here. I don't want to have two functions. So we'll do each one 20 times, and then we have a quit function. This is all from the vignette to the package that is available with the download of the package. So to start the cluster, we say we want to look at the GUI, and this is our path. Again, I'll show you the path. It's where our Netlogo is, and inside of that, the model path is as follows. Here. Now what we can do with this next bit of script, invisible, and using the par-lapply, which is a parallel script, a parallel function. Over the cluster we created, over the 4 processors, we can run the following function, which is pre-pro, which is set up for each processor, set up a model. And you can see above what it is doing is it's starting and loading the model. So we're going to have 4 of these running at once, not just one now, because we have 4 processors. So I'll run this, and I'm going to just switch to my desktop so you can see they should start appearing. Again, this is a bit slower because I think I'm grabbing the screen, and that slows it down a bit. So there's number 1, number 2, number 3, number 4. And if you bear with me, I'm going to resize these so we can see all 4 at once. I'm not going to get too obsessive about making them all neat. 1, 2, this is the 3rd one. It goes up there, and the 4th one. Now what we're going to do is we're going to send a job to this little cluster and get it to do what we just did, i.e. run for each of the 11 densities, 55 to 65. We're going to get it to run 20 simulations for each density, using the function above, again using par-lapply, which is the parallel function. And so it will send to each one, and there it's already done it. You can see the top left is at density 58, top right is density 55, bottom left 61, bottom right 63%. It's running 20 simulations for each density, splitting the job over the 4. I'm going to unclick view updates to make it faster, and I'll come back. Okay, so we're just waiting for that top left one to finish. This job took a bit less time than the previous one. We'll go back to R in a moment. So that job took me about less than 5 minutes, and again, grabbing the screen, it takes longer. So let's look at the results we got from that. In this results.par object. Actually, I'm just going to delete this because it's technically not what happened. There's actually a trick you could do as well. For models, usually there's 1 or 2 parameters that are going to take longer. We could have scrambled the sequences of densities so that each one didn't have to do all the heavy lifting. We could have done it differently. Anyway, we've got 11 items in this list, and there they all are. Each one is an independent run of the model at a particular density, and I'm just going to put that into a data frame and plot the results. And we get the nice box plot, similar to above, but just a ggplot version. But this took much less time because we did it in parallel. And I could have made it faster too by deciding which processor got which density. Okay, but when you quit Netlogo using parallelization, you need to quit all of them, not just one. So this is the code we use for that, and we stop the cluster. So that's a brief introduction. I'm just going to save my work. That's a brief introduction. I'm now going to move to the second model. And this is the sheep and wolf model. So again, this is a standard model used to teach Netlogo. We'll find it in the models library under biology and evolution. There it is, wolf-sheep predation. And There's lots of different things we can manipulate on the left-hand side with these sliders, but essentially it's a world in which there are sheep, there are wolves, the sheep eat grass, the wolves eat sheep. Depending on who's available, sheep will reproduce or wolves will reproduce, and over time you can see here the sheep are reproducing, but now they get eaten by the wolves start to increase in population size, the sheep go down, and this time all the wolves ate the sheep and then all the wolves die because there are no sheep. Let's start again, run the model again using the same parameters. Sheep increase, they eat the grass, they reproduce, now the wolves eat the sheep, but this time one sheep makes it through, starts reproducing, and the sheep inherit the earth, and there are no wolves. So it's looking at cycles in population dynamics, and there's lots of things we can change. For instance, this wolf reproduce slider, this is the percentage of the rate of wolf reproduction basically. So we go, and this is a lower reproductive rate, so the sheep take over much fast, larger population size. It's a struggle for the wolves to make a comeback, but here they are, they do eventually, and again they've eaten all the sheep. See 0 sheep left. Okay, here's the code, global grass. We have 2 breeds, we have sheep, we have wolves. Each of the turtles, the sheep and the wolves, have something called energy. The patches can regenerate, that's what that's doing. And again we have a setup function. All these things happen on setup, and a go function, and various other functions. And oh, I should say all of these examples I've used are by Yuri Valensky. Okay, so in the R code, again, RJava, RNetlogo, and set the working directory to the RNetlogo folder. We'll make a path. This is the link, and we'll start a model. Just doing one at a time. It should appear. Through R we have loaded Netlogo. Here it is. We haven't set up yet, we have to hit NL command setup. And once we do that, I'm just resizing this so you can see. Setup. There we go. Some sheep, some wolves, and we'll do 150 ticks. NL do command 150 go. And there we go. The model is running. Now what I want to show you with this is that for each, we can use this NL get agent set information to essentially get any piece of information that belongs to the turtles, in this case all patches, but I'm doing turtles here. And I want to know the X and the Y coordinates. So just looking at the help guide here, you can see it says report variable values of one or more agents as a data frame or list or vector. And this is great. We could have picked energy, actually. That was one thing we could look at. So first of all, we need the variable, and then we need the agent set. So in this case, I'm not picking energy. I'm picking X and Y coordinates of turtles, which are sheep and wolves. Sheep and wolves. And here it's returned it as a data frame. So there are 126 of them after those 150 ticks, and this is where they exist in the world. And I'm now going to use NL report just to list the minimum and maximum coordinates of the world. And in settings in Netlogo, I just click settings, you can see that it tells you the max and minimum coordinates of the world, 25, 25. But we're better to get that through using this function, NL report. And this is the this is the Netlogo code. So we've now got that, and it's minus 25, 25, the dimensions. And simply just going to plot the world and plot the location of the animals in the world. So we've grabbed that information and we can plot it. And you can see that those dots are the same. To make it more interesting, I will just grab separately for the sheep and for the wolves where they are. Again, this is just the spatial coordinates. We could have picked energy or anything. And I'll plot them using base R. You can see, yeah, we've recreated, and the blue dots there represent where the sheep are in the world, and the red circles are the wolves. So we could recreate movement over time if we wished, or we could recreate anything to do with the attributes of the agents by using this get agent set thing. All right, the next thing, let's just do this do report function again. I just want to show you how we can reproduce that graph in the bottom left, the populations. So let's make a new model, set it up, and do report for 150 ticks, count sheep, count wolves. That's Netlogo code, and it's going to run a model, and for every tick it's counting the sheep and it's counting the wolves. And we're returning that as a data frame with column headings sheep and wolves, and I'll just do a simple reshape in a minute. There we go, number of sheep, number of wolves, all the sheep died off. 150 ticks. Let's reshape. And it's just one column with the value that we're going to plot, just so we can do a ggplot like this. Zoom in, and, well, the colors are reversed, but we can change that, and you can see it's the same. So that's great if we wanted to rerun the model many times, which I will do. So I'll just quit, and I'm going to restart the R session so we can change one of the sliders. Okay, so we had to do this. We have to restart our session because we're going to run a model again. We have to set up with the libraries, set the working directory. I'll go down to the script. And we're going to do this in parallel to make it faster. So again, run the parallel library, detect cores, make a cluster. Again, I know my laptop has 4. And we'll do the 3 functions, the initialization, same code, just starting and loading a model. The sim function, in this case, I'm going to say set the wolf reproduce slider to this variable WR. I'm going to vary the reproducing percentage, the rate of reproduction of the wolves, and set up. We can count the number of sheep and wolves over time with this varying rate. So we'll do 200 ticks of the model, and then we'll count the number of sheep and wolves dependent upon the wolf reproductive rate. And here's, again, just start the Netlogo model 4 times because I have 4 processors, and it should pop up 4 times. Again, you're going to have to bear with me resizing windows awkwardly. You could run this without the GUI showing. It would be slightly faster, I believe. It's called headless mode, but I just think it's worth just showing the 4 in action. So here's window 1, here's window 2, and 3. And 4. Okay, so we have 4 Netlogo models. Now, here's the code to do this. All we're going to look at is from 0% to 10% in increments of 0.2. And we're going to run the model using parseApply over the cluster, changing that particular variable, collecting the data for every 200 ticks. How many sheep and how many wolves with this one parameter that we're varying. And I'm going to run it, and then I'm going to show you the 4 models quickly. There you go. You can see the one on the top is running at 2.6% wolf reproduce. The one on the bottom left is at 0%. The sheep are doing pretty well. The one on the bottom right is at 5%, and the one on the top right is currently at 7.6%. So I'll just unclick View Update so this will run faster, and then I will come back as the model is finishing. So it's finished. That didn't take very long. It took a few minutes, if that actually. Here we go. Here are all the results. And this little bit of script here is just to tidy up those data. There's 400 rows because there's 200 sheep counts and 200 wolf counts for every tick, 1 to 200. And I'm just going to make a data table because it's easier for me, at least. And there we have 20,000 rows from varying those 51 different wolf reproduce parameter settings, And this is exploratory analysis, this is not how I would necessarily look at the data, but I'm just going to create some faceted ggplots. So we're looking at counts of sheep and wolves here, and the darker colors indicate lower wolf reproducibility levels. So in the sheep you can see when the wolves reproduce a lot, basically the sheep don't have a standard chance, and when the wolves don't reproduce at all, the sheep go ballistic. But in between there's intermediate values, and on the right the wolves, there's definitely something about the rate at which the wolves show this peak and decline changes at different times depending on their reproducibility rate. There's a time shift, it goes to the right, with decreasing wolf reproducibility values. So this is not something you would publish, but it's interesting for exploration. Let's just look at this in a slightly different way, looking at each wolf reproduction rate and looking at the plot, looking at the number of sheep and wolves on the same graph. It's going to take a little bit of while. Just zoom in here. My computer's a bit slow because of the screen grabbing, I think. And what we can see from this is if the wolf reproduction rate is so low, the sheep just increase their population rapidly. But for most values, there's this cycling, but the degree to which there's relatively more sheep or wolves is dependent upon this wolf reproducibility rate. So finally, we just close it the same as before, and by closing the cluster and closing the Netlogo windows that are open. And that's pretty much it. I hope you enjoyed these tutorials. The code is available on my website and GitHub, and any questions, please get in touch.